Okay, we are ready to begin today's lecture. So last time we talked about estimation for the simple linear regression model with just one explanatory variable, x. Okay, so let's remind ourselves of where we were, and then we will talk about how to do inference, and in particular we're going to review some of the properties of the normal distribution, and we'll introduce the chi-square and the t distributions. Okay, so here is the model. So we have the data points. So remember, they are pairs. We observe the pairs xi, yi, and then we conceptualize this probability model for the response. The ith response yi, it's a normal distribution. The mean is given by the regression line. Okay, so we conceptualize the mean is given by beta 0 plus beta 1 xi, and variance sigma squared. Okay, and so this is the theoretical model, and so after we collect the data, we fit the model. In other words, we estimate the parameters beta 0 and beta 1. We obtain the equation of our fitted line. Okay, so this is the model, and then the equation of our fitted regression line. Okay, so we drew a little picture last time. So what the line on that we have fit to the data would be described by this equation, y equals beta 0 hat plus beta 1 hat x. Okay, so beta 0 and beta 1 hat. Okay, so these are the estimates of these unknown parameters, beta 0 and beta 1, computed from the data. And last time we explained how to get those estimates based on n observations, xi, yi. Okay, so to pick up from there, let's talk about the interpretation of the parameters we see in this equation. So we have the two regression parameters, beta 1, and then we have a variance parameter sigma squared. So we're going to talk about those next. Okay, so I'll call this interpretations. All right, so we're going to work through these three parameters. Okay, so first we have beta 0. Okay, so how do we interpret our estimates? Remember when we talk about the estimate, we put a hat on top to distinguish it from the true but unknown parameter. Okay, so beta 0 hat is our least squares estimate for beta 0. Okay, so how do we interpret this? Okay, so we can write it like this. It's the estimate. So it's the estimate. Okay, so estimate refers to that this is the beta 0 hat. Okay, so this is the estimate of what? Okay, so beta 0. So if you look at the mean part of this normal distribution, beta 0 is the expected value of y when x is 0. And so we can interpret it as the estimate of the expected response when x is 0. Okay, and then we see that, in terms of the graph, we know that beta 0 hat is the y-intercept of our estimated regression line. Now, of course, we have to be careful when we interpret it, because sometimes the x equals 0 is not even meaningful. So let's put a little caveat here. So this is, but we should not be too careless to interpret it, because it might not be meaningful. And so let's add this point here. So if the range of your x's doesn't even include x equals 0, then we should be careful when we try to extrapolate outside the data. Okay, so the interpretation not necessarily meaningful if outside the range of the x's in your data. Okay, so that's beta 0. Okay, so the other parameter is beta 1. So let's talk about its interpretation. So that's beta 0, so beta 1 hat. So again, it's an estimate. So it's the estimated estimate of. Okay, so now we can see from the equation that it corresponds to the slope of our straight line, and so as we understand from equation of a straight line, we increase x by 1 unit, then y, the change in y would be governed by the slope beta 1 hat. Okay, so we can write it this way. So beta 1 is the estimate of the expected change in the response when we increase x by 1 unit. So I'll say for unit increase in x. Okay, so that we can get from what we know about equations of lines. So that's the interpretation of the slope parameter beta 1 hat. Okay, so how do we calculate beta 1 hat? So remember we had this expression. So based on n pairs of data, we calculate this quantity xi minus x bar, yi minus y bar. And on the bottom, we have xi minus x bar squared. Okay, and the summation goes over all data points, so 1 to n. And so in terms of a couple of shorthand notations that we defined when we talked about correlation, we called this, we can denote this, so the top part is, our shorthand is the sum for the xy cross term, and then the denominator is the x term with itself, so we write S subscript double X. Okay, so from previous shorthand. Okay, so we've talked about beta 0 and beta 1, so that leaves sigma squared. Okay, so what is sigma squared? Well, it is, okay, so let's remind you, so sigma squared, we can think of as the variability around your regression line. Okay, so that's loosely what we can interpret it as, because we think of the observations as the model for observations is the average expected value is at the line, and then there's some variability around it, and so sigma squared is a measure of that variability. So recalling from the model, sigma squared is both the variance of the variance of the error term for every I. So from I from 1 to n, we assume that the same error variance describes all of those points. And so we also know from the model that this is all variance of epsilon is also the variance of yi. Okay, so how do we estimate sigma squared? So we notice that because it's associated with the variability around the line, let's look at the error terms. So we've seen both. We've defined both epsilon and also we've also defined the residual. Okay, so let's connect them together next. Okay, so how to estimate okay, so let's compare the two notations. Let's write them side by side. So remember that when we think of the error term in our model, so epsilon I, if I rearranged what I wrote at the beginning, then we can think of epsilon as being the difference between the random variable, so the model for yi, minus the model the regression line for the model, so that's beta 0 plus beta 1 xi. Okay, so that's by definition epsilon I. Okay, so this comes from the model, and the key thing here is that this is a random variable because we're looking at it from the modeling perspective. That's why I have capital YI here. So we're talking about the random variable, and then we're talking about the model unknown values for beta 0 and beta 1. So this is our conceptualization for data, and epsilon I refers to that error term. Now, after we have fit the data, we calculate what I called last time the residual. Okay, so that I used a different notation for. I call that E sub I. Okay, so how do we calculate the residual? We calculate it from the actual data and the estimates. Okay, so I take the actual data values in my that I observe. So this is lowercase yi, and then I subtract off what I called last time the fitted value. So that's the equation of the regression line, but with the estimates plugged in. Okay, so that's beta 0 hat and beta 1 hat. Okay, so that's the difference between epsilon I and EI. This is from the model, and then EI is calculated the values calculated from the data. Calculated from the data. And so we have these, so we want to write these side by side so you can see the difference. And so now we need to use what we can calculate. So we're going to use the EIs to estimate the unknown variability around the line sigma squared. Okay, so intuition then is we will use the variability in our residuals. Okay, so those are the E's. Okay, to estimate sigma squared. And in fact, the variance in the residuals, you could imagine, should be similar should be a pretty good guess of what the actual variance is. So again, we're going to use the sample to estimate this parameter. Now, when I was an undergrad, one of the more confusing concepts here was, well, how do we know what to divide by? Okay, so let me write down the estimate first, and then explain where when we first see it, we often have questions. Okay, so we use the estimate as follows. So sigma squared, I'm going to estimate it. So I'll put a hat on it. So this is going to be our estimate of sigma squared. Okay, so let's write down an expression that looks like the variance of EI. Okay, so remember EI we calculate on n data points. So we can imagine writing down the sample variance of the EIs. Okay, so we would start like this. Okay, so sample variance formula starts like this. EI, okay, I'm going to subtract E bar, okay, squared, sum, and then I'm going to divide by, well, normally if you're calculating sample variance, you would divide by n minus 1. Okay, except in this case, we're going to divide by n minus 2. Okay, so I'll explain that in a moment. But suffice for now to say that this looks like, okay, so this looks like the sample variance of the EIs. Okay, so that's the estimate. So we'll make one simplification here. So this is actually equal to simply taking the EI squared over n minus 2. Okay, so why are these two equivalent? So let's do a quick check. Okay, so what is E bar? Okay, so I mean this is to take the average over all the EIs. Okay, so I'm going to take the average. So look at this equation. I'll take left hand side, take the average, becomes E bar. Okay, what happens if I take the average of the right hand side? Okay, so the average of all the YIs is Y bar. And I need to take the average of all of this stuff. Okay, so So these are just constants, so you still have beta 0 hat. And then the average of beta 1 hat xi is simply requires you to take the average of all the x's. So that's beta 1 hat x bar. Okay, and then this thing is actually just 0. Okay, so why is it just 0? We'll look back at our notes and we'll see that if we just plug in our estimate for beta 0 hat, then that cancels off the y bar and the beta 1 x bar term. Okay, so that's why the e bars or e bar is 0. By definition of our beta 0 hat estimates. Okay, so therefore we just end up with this thing. So basically, what is this? Is to take all the residuals, you square them, and then we sum them up. Okay, so that is the numerator, and the denominator has this funny-looking n minus 2. Okay, so let me describe that next. So this thing on the top, we can call that the sum of square residuals. So we can abbreviate to take all the residuals and square and then sum. So we can abbreviate that by SS. Okay, and then in brackets we can put res as short for residual. So that's the numerator. Okay, but what about the denominator? Okay, so as I said, this looks like the sample variance of the EIs, except I'm dividing by n minus 2. Okay, so this is related to the concept of degrees of freedom. Okay, so we will look at that in more detail, and it'll become clearer when we look at the linear algebra behind multiple regression. Okay, it is it's called the degrees of freedom, and we will see that in more detail later. For now, let's suffice to say how we got the n minus 2. So I'm going to abbreviate by degrees of freedoms. So we calculate it by taking n minus the number of parameters estimated, params. Okay, so there's 2. We estimated beta 0 and beta 1. Okay, so those are our 2 model parameters. So we subtract 2 from the number of data points. So n minus 2. So that's one way to explain it. The other one, which I think is probably more intuitive, is to ask, well, what happens if we think of sigma squared hat as a random variable? Okay, and we're gonna do that with beta 1 hat in just a second. But you think of this as a random variable, it would have a mean and a variance. Okay, and so what we achieve by dividing by n minus 2 is we make this guy sigma squared hat an unbiased estimate of the true sigma squared. Okay, and so let's talk about this n minus 2. So it allows this to be an unbiased estimator. Okay, so E of sigma squared hat actually works out to sigma squared in this case when we divide by n minus 2. So that's true, which means in the language of inference, sigma squared is unbiasedly estimated. So unbiased when sigma squared hat is viewed as a random variable. Okay, so that's what I'll say about the n minus 2 for now. So think of it as the number of observations minus the number of estimated model parameters. So that's beta 0 and beta 1, and then it has the mathematical property that it gives us an unbiased estimate for sigma squared. And then we're going to generalize and talk about degrees of freedom a little more when we do the linear algebra behind multiple linear regression. Okay, so those are the 3 parameters, and so I've given you some interpretation and intuition for how we use those 3 parameters. So we have the intercept, the slope, and then we have a measure of the variability. Okay, so now we're ready to look at inference. Okay, and so the motivating question then is, okay, so suppose we've calculated estimates for beta 0 and beta 1. And so we naturally might ask next, well, what is the size of beta 1 hat? I calculate from the data, but is that linear relationship statistically significant? Okay, and so in order to do that, we need to use the properties of the normal distribution and then chi-square and the t distributions. Okay, so we'll call this section so inference. Okay, and so a motivating question is this linear relationship statistically significant? So is there a statistically significant relationship between x and y? Okay, so in order to do that, we're going to take a closer look at our estimate, beta 1 hat, because this is the parameter that tells us how y changes with x. Okay, so I'm going to leave this guy here for a moment. I'm going to look at this as a random variable and show you how to do that. But before I need a little fact about normals. Okay, so here's a fact about normal distributions. Okay, this can be proved using a moment generating function in stat 330. But all we need is to be able to use it here. So let me just state it. So suppose we have a bunch of normals. Okay, so let's use yi for a bunch of normal distributions. So each one can have its own mean, mu I, and potentially its own variance, sigma squared I, and they're all independent. Then the fact that we're going to make use of here and in the future as well is that a linear combination of independent normal random variables is also normally distributed. Okay, so let's write it as following. So we're going to take constants ai and multiply each yi by some constant and then sum them up. Okay, so there's summation ai yi. Okay, so this also has a normal distribution. And how do we get the mean and variance? Well, we simply calculate the mean and variance of this sum, and it is in fact normal with that specific mean and variance. Okay, so the mean of this, so the expected value of this summation would be simply this linear combination of the means, so ai mu I, and then with them all independent, we get the variance here by taking the variance of this sum. Okay, so when you take variance, the constants become squared, so you have ai squared, and then the variance of the yi's, each yi is sigma squared I. Okay, so that's a very useful fact about combining normal distributions in a linear fashion. For any constants ai, so in words we say that a linear, so how to remember it, linear combination of normals is normal. Okay, so that's how we can state this fact in words. Okay, so with that in mind, we're now ready to look at the distribution of beta 1 hat, and we view that as a random variable. Okay, so I'm going to start with the expression for beta 1 hat, and I'm going to write it in in a couple different ways to make our computations a little easier. Okay, so let's start from the way we wrote the estimates, so xi minus x bar. And I'm going to review it as a random variable, so I'm going to use cap y now, yi minus y bar. And on the bottom, you have xi minus x bar squared. Okay, so let me remind you that for our purposes now, we are going to treat the x's as simply constants, so they're not random variables. So I'll always be writing these x's in lowercase. Okay, so preamble for this, we can say review beta 1 hat as a random variable in this random variable form. So we have the random variables in this expression are yi and y bar. Okay, so I'm going to slightly rewrite this to make our computations, our coming computations a little easier. So I'm going to break up the sums in both the numerator and the denominator. Okay, so I'm going to write summation xi minus x bar. I'm going to do yi by itself. And then I'm going to pull out the second term, so y bar I'm going to pull out. So y bar does not depend on the summation, so this is sum from 1 to n. Y bar doesn't have the index I, so I can pull it outside. So I have y bar summation xi minus x bar. Okay, and the reason for doing so is because summation xi minus x bar, you should convince yourself that by definition of x bar, this thing is 0. Okay, so this goes away because this is just 0. And why? Because both of them sum to n times x bar. Okay, so you can see that by definition of summation. Okay, so in other words, my numerator can be expressed as in this way. So summation xi minus x bar times yi. Okay, I'm going to do a similar thing on the denominator. So we have summation. So I'm going to expand this. So imagine writing xi minus x bar twice. So I'm going to have a similar expansion. So I have xi minus x bar xi, and then the second term will be the x bar pulled out, and then summation xi minus x bar. So again, by the same logic, the second term is 0. Okay, so I have this slightly more convenient expression now for beta 1 hat. Okay, it looks like this guy, and that's the one I'm going to work with. Okay, so as I'm setting up this calculation, let's look at this expression and convince ourselves that this is in fact a linear combination of normals. Okay, so why is that? Well, each yi is a normal distribution, and so it looks like there's a whole bunch of stuff in front of it, but really we can just view this whole bunch of stuff as just a constant. So it's a summation of constants times yi. Okay, so that's the key fact that we will use from this expression. And so we combine it with what we said about normal distributions, that we have this, we're going to use this fact on this expression for beta 1 hat. Okay, so there's two things to note. First, it's a linear combination of normals, therefore beta 1 hat is going to have a normal distribution. And using this fact, we can compute the mean and variance of this expression. Okay, so we're going to compute E of beta 1 hat and its expectation and variance. And once we've done that, we know that beta 1 hat is normally distributed with that mean and variance. Okay, so in other words, we have already shown now that beta 1 hat can be written as the summation of a bunch of constants times the yi's. Okay, so which is what allows us to apply this fact where, okay, so what are the constants? So we have to look a little carefully at here. So what do we need to plug in for ai here? So we have summation here. So we have summation something times yi. So what is this thing? Well, the denominator is the same for all of them. This is the denominator, and then the constant out here is xi minus x bar. And so we see that the required constant is xi minus x bar over the summation in the denominator. so that's the expression. So now we're ready to take the mean and variance. Okay, so we take the expectation of this. So here we have to remember from our first stats course that expectation is a linear operator. Okay, so our expectation of a summation, I just have to add up all the expectations and pull out the constants. And so we have summation AI and then E yi. Okay, so that's according to linearity of expectation. And then I just need to plug in, well, what is the expectation of yi? Okay, so remember in the model, what gives the mean of yi? Well, it's the value of the regression line. Okay, so this is beta 0 plus beta 1 xi according to our hypothesized linear model. So we can plug that in, and then we're going to use this value of ai, and then we're going to simplify everything. Okay, so let's do that over here. So we have summation xi minus x bar, and then we're going to have beta 0 plus beta 1 xi. And then the denominator is xi times xi minus x bar, summation. Okay, so this is what we need to simplify. And so again, we're going to use properties of summations to help us work through this. So we're going to break this up two terms. So we have beta 0. So beta 0 is a constant with respect to the summation. So we can pull that out. So that's the first term. And then the second term, we have beta 1. So that pull that out. And then we have inside the summation, we have xi minus x bar. Okay, so now we see the reason why I wrote it this particular way, because again, this part, okay, again we see this xi minus x bar summation, so this is 0, so you can ignore this part, there's nothing involving beta 0, and so now we look at what's left over. Well, you have beta 1 times this bunch of this constant, and then on the bottom you have exactly the same constant, and so that constant cancels, and we have our answer, it's simply beta 1. Okay, so that's good. So what does that tell us? So our estimate, beta 1 hat, on average, so this is viewing it as a random variable. Okay, so on average, it's going to have value beta 1. Okay, and so what do we call this? It's an unbiased estimator. So on average, the estimates will give us the correct value for the true unknown parameter. Okay, so that's the expectation, and then now we need to do the variance. Okay, so we have E, and then now we have variance, beta 1 hat. Okay, so again, we use the fact that all the yi's are independent, and so we can do the variance on the sum. So we have summation, and the constant's ai's, so that comes out squared, and then variance on yi. Okay, so again, according to the model, what is variance yi? Well, remember, y is normally distributed with mean given by the regression line, and then variance given by sigma squared. So we can plug in sigma squared here. And then we just need to simplify this thing. Okay, so we'll write it like this. So I can pull out sigma squared. Okay, so ai, summation ai squared. Okay, so I'm going to have summation. I need to square ai, so I have xi minus x bar squared. Okay, and then on the bottom, I'm going to have this whole thing squared. Okay, and then now we just need to go backwards. So to simplify this, you look at this denominator and you realize, well, I mean, we can just replace this by what we had originally. So this is sigma squared I minus x bar squared. And at the bottom, let's just replace this by the xi minus x bar form, which already showed to be equivalent. And so you simply have this thing squared. And so one of them cancels. Okay, so we have our final answer is sigma squared over this summation. And I'm just going to use our shorthand for it. So this term is the sum of the x cross term. So we just use that shorthand here. Okay, so we have found the mean and variance of our slope as a random variable. So finally, we just need to apply the fact about the normals. So not only does beta 1 hat have this mean and variance, but it is normally distributed with that mean and variance because it is a linear combination of normals. So to finish off, so since beta 1 hat is a linear combination of normals, we can write down this distribution. Specifically, it's normal with mean beta 1, so in other words, it's unbiased, and variance is given by this expression, sigma squared over the sum of squares for x. Great, so that's the final result for beta 1 hat. Okay, so the reason we did the calculation for beta 1 hat first is because that refers to the to our slope, and so the slope parameter is what's going to help us determine in this case whether there's a significant linear relationship between x and y. But you can also imagine doing a similar calculation for beta 0, so I'll give you that result, but we won't go through the details of that. So in a similar way, we can look at beta 0, so similar calculations give the distribution for beta 0 hat. So viewing beta 0 hat as a random variable, we can also calculate that it has a normal distribution with mean beta 0, and variance is given by this expression is sigma squared 1 over n plus x bar squared over the sum of squares x. Okay, so this can be done using by similar techniques. So in other words, both the beta 0 and beta 1 estimates are unbiased estimates. Okay, so having derived these estimates and their distributions, we are now ready to ask the question. So use these distributions and use these to decide whether the estimates are statistically significant. Okay, so we're well on our way to doing that, and so we are going to first standardize, and then we're going to compute test statistics and confidence intervals to decipher whether beta 1 hat is statistically significant. Okay, so let's start. So let's take this expression, beta 1 hat, and let's apply standardization. Okay. So we take beta 1 hat. Okay, so this is view it as a random variable because I'm going to subtract the mean. That's beta 1. That's the unknown parameter. Okay, and then if I divide by the standard deviation of the normal, so So that's the square root of this. Okay, so I'll put sigma over the square root of the sum of squares x. Okay, so then this is equivalently a standard normal distribution. In other words, a normal with mean 0 and variance 1. Okay, so this is the basis of how we do inferences on the slope parameter, because we know that this quantity has a normal distribution, and so we say intuitively that the slope is statistically significant if it is not 0. Okay, so we're going to be testing the hypothesis of whether the slope parameter is significantly different from 0. Okay, so it looks like we're almost ready to come up with the test statistic, but we have a slight problem, and the problem is we can compute this quantity. And the reason is this has a sigma in the denominator, and we don't know what sigma is. So the best we can do in general is to plug in our estimate for that. Okay, so sigma is, however, unknown. So we're going to have to replace it with our estimate for it. So need to estimate sigma hat. Okay, so I'm going to rewrite this again, which leads to this expression. So I'm going to have beta 1 hat minus beta 1. And then I'm going to have sigma hat over root of sum of squares x. Now, once I make this replacement, however, this is no longer a normal distribution. In fact, this is going to be a t distribution, so I'm going to just briefly explain that. But one thing I want to note here is, so what do we call this thing on the bottom? So this part. So sigma hat over root sum of squares x. Okay, so if you look at this expression, beta 1 hat, what's the standard deviation of beta 1 hat? Well, it's this part in the denominator, right? So sigma over root sum of squares x, this is the standard deviation of, so this is standard deviation of beta 1 hat. Okay, so what have we done is we don't actually know the standard deviation. So what we've done is we have plugged in an estimate for sigma hat here. Okay, so the way we call this part is now a standard error. Okay, so standard deviation is sigma over root sum of squares x, and since we have estimated this standard deviation, we call it the standard error. Okay, so this is what we call the standard error of beta 1 hat. Because it's the estimated standard deviation of beta 1 hat. Okay, and so to estimate it, we have plugged in sigma hat here. Okay, so this is what I mean by standard error of beta 1 hat. Okay, so now I need to show you the basics of why this ends up being a t distribution, and to remind you of what is a t distribution. Okay, so I'll write down the result first. So this is a t distribution with n minus 2 degrees of freedom. But I'm going to go over here and define for you what the t distribution is and how we get this result. Okay, so a random variable or construct a random variable using this form. So I'll call it capital T. So I'm going to construct it by taking a standard normal, and then on the bottom I will divide it by the square root of a chi-square. So expressly in this form. Okay, so I'm going to define a random variable t in terms of two other random variables, a z and a u, where z is a standard normal, and u is a chi-square with k degrees of freedom, and they are independent. z and u are independent. Okay, so when I define a function in terms of these two random variables in this form, so z over root of u divided by its degrees of freedom k, this defines what we call the t distribution with k degrees of freedom. Okay, so this is t distribution with k degrees of freedom. Okay, so that's the construction of the t distribution. And now you notice there's a chi-square here, right? So I need to give you one other fact so that this whole thing makes sense. So a chi-square, so a chi-square, 1 degree of freedom, you simply take a standard normal and you square it. That defines a chi-square. So the fact that we need to use here is that there's a chi-square distribution associated with our estimate for sigma squared. Okay, and so this is this definition of the t, and then we also have another fact. So the sigma squared estimate that we defined earlier. So if I multiply that by its degrees of freedom, so that's in this model it's n minus 2, and then divide by sigma squared. So for simple linear or this simple linear regression model, this quantity, which is also simply just the sum of squares residual divided by sigma squared. Okay, so remember sigma squared, the estimate for sigma squared is sum of square residual divided by n minus 2. Okay, so this numerator is really just the sum of square residual divided by sigma squared. This has a chi-square n minus 2 degree freedom. Okay, so with those two facts, I can show you how we get from this normal to this t distribution. Okay, so let's do that here. So how am I going to get there? Well, I'm going to use this. I'm going to take this result and use it in our construction of the t distribution. Okay, so I will don't need this. No. Okay, so we will start from this expression. And so I'm going to manipulate it. So let me just write it first. Okay, so what I'm going to do on the top is standardize. So I'm going to put sigma over root sum of squares x. And so so if I'm doing that on top, I've got to do that in the denominator as well. And so I'm going to have this. I'm going to put everything inside a bigger square root, so it's clear. Okay, so in the denominator. Okay, so originally I had sigma hat, so I'm going to have sigma hat squared. And I'm going to divide by sigma, so it's inside the square root, so it's sigma squared. And so to manipulate it into this form where it looks like this, I'm going to multiply by n minus 2, over here, and then I'm going to divide by n minus 2. Okay, so with that, we can convince ourselves that this is in fact equivalent. Okay, so the only thing we've done here is move things around, and then we divided by sigma in both the numerator and denominator. Okay, so therefore this cancels out to the left-hand side. And the reason for this expression is now we can see where the t distribution comes from. So this top part, okay, as we mentioned, this part is a normal 0, 1 from the fact about beta 1 hat. And then this thing in here, okay, so by this fact about the chi-squared, this one is a chi-squared n minus 2, and it's divided by its degrees of freedom, n minus 2. And so now we have exactly the construction for the t distribution. We have normal on top, and then we have root of a chi-squared divided by its degrees of freedom on the bottom. And in fact, it can also be shown that these two are in fact statistically independent, and therefore this defines a t distribution n minus 2 degrees of freedom. Okay, so we're not going to show that here, but can show these are independent. Okay, so that's a brief explanation for why, even though beta 1 hat has a normal distribution, when we actually do inference, so when we compute confidence intervals for beta 1, and when we do hypothesis tests on beta 1, this is why we use a t distribution, is because sigma has been estimated. Okay, so the last thing I want to do today is simply to run through how to do the confidence interval construction and how to set up a hypothesis test. So hopefully you've seen elements of this in an earlier stats course, but I will run through all the steps here so to remind you of how these concepts work. So two concepts: confidence interval and hypothesis test. Okay, so first one is confidence intervals for beta 1. Okay, so to motivate this, well, let's draw a picture of the t distribution. Okay, so let's draw a t n minus 2 distribution. So in terms of shape of the distribution, it's much like the normal, except as you may have heard, the tails are fatter. Okay, so there's more density in the t distribution in the left and right tails compared to a normal. Okay, but otherwise it is symmetric and it has its peak at 0. Okay, so when to construct a confidence interval, we need to use what we call quantiles from the t distribution. Okay, so for example, you might want to do a 95. And probably the most commonly used is a 95% confidence interval. And so because we know that beta 1 hat divided when it's standardized using the estimated variance sigma, we get a t n minus 2, so we'll be using quantiles from this distribution for that construction. Okay, so I'm going to label this graph. So let's put a constant c, so it's symmetric. So c and minus c, so there's an equal amount of area under the curve here. Okay, so generally we use alpha to denote confidence level. Okay, so we want a 1 minus alpha confidence interval. We're using this central part of the t distribution such that the area under this part of the t distribution curve is 1 minus alpha, and then the bounds are symmetric from minus c to c. Okay, so I'm going to abbreviate confidence interval with CI. So a 1 minus alpha confidence interval for beta 1 is given by this expression. So we'll take the estimate beta 1 hat, and then plus minus constant times the standard error of beta 1 hat. So that's the general construction of a confidence interval. So these quantities, beta 1 hat and its standard error, are calculated from the data. And then we just need to specify what is this constant. Okay, so this constant is going to depend on the level you want. So it's going to depend on the 1 minus alpha. And it's also going to depend on the reference distribution, which in this case is the t with n minus 2 degrees of freedom. And so we need to define what is this guy c. So we're okay. So how do you specify c? So we'll write it in words. Okay. So it is the quantile of the t distribution such that how much area is to the left of c. Well, you have 1 minus alpha under the curve, and then that's going to, and due to symmetry, that's going to leave alpha over 2 in each of the two tails. And so c is the 1 minus alpha over 2 quantile of a t n minus 2 distribution. In other words, the probability that the absolute value of the t distribution is less than equal to this cutoff point c is 1 minus alpha, or equivalently, the probability that t without the absolute value is less than c, it would be 1 minus alpha over 2. Okay, so this random variable t is where capital T here has this t distribution with n minus 2 degrees of freedom. Okay, so that's the confidence interval construction. We use the middle parts of the t distribution, and due to symmetry, we have c and minus c, and that defines the bounds of how we get 1 minus alpha probability. Okay, so the flip side of that is the hypothesis test. Okay, so here to ask, is there a significantly is there a slope that's significantly different from 0? We would ask the question of whether this null hypothesis of beta 1 equals 0 is supported by the data or not, versus the alternative, which is that the slope is significantly different from 0, in which case we conclude that there is a non-negligible relationship between x and y. Okay, so then let's walk through the steps and the reasoning of the hypothesis test. Okay, so we start like this. So if the null hypothesis is true, then what distribution do we have? Okay, so remember this was the t distribution, beta 1 hat minus beta 1 over the standard error of beta 1 hat. Okay, so if the null hypothesis is true, then we can plug in the null hypothesis value, beta 1 equals 0 in here. So this would be beta 1 hat over its standard error. So this would have a t distribution n minus 2 degrees of freedom. Okay, and so how is that useful? Well, this is the quantity we can compute, so we can use this as a test statistic. Okay, so calculate. What we can do then in practice, we calculate the value t. I'll call it test statistic here, beta 1 hat over its standard error. Okay, and so we take this. So this picture helped us helped us visualize where the confidence interval comes from. And so the hypothesis test is like the flip side of it. So, so I draw another picture. So the intuition behind the hypothesis test, so I'm going to draw the same thing, but with a different emphasis. Okay, so again, I'm going to have minus C here and C here, the symmetry. Okay, so as I mentioned, if there's 1 minus alpha in the middle, then due to symmetry, there is 1 minus, there's alpha over 2 probability. In the left tail, then there's also alpha over 2. In the right tail, and then there's 1 minus alpha in the center. And so intuitively, well, when are we going to conclude that the null hypothesis is to be rejected? Okay, so this test statistic tells us the distribution of gives us a distribution when the null hypothesis is true. Okay, so when the null hypothesis is true, this follows a t distribution, and so most of the time the values are going to come. You imagine this to be a random variable, and so with a value drawn from this distribution, so most of the time it will fall in the middle of this distribution, and on occasion, if it's true, it will fall in the tails. And that's the intuition behind the hypothesis test. So if we observe a value for t that doesn't appear to be consistent with the null distribution, that's when we reject the null hypothesis. And so we treat the tails as evidence then that this test statistic did not come from a t distribution. So in other words, if this observed value is very far to the right or very far to the left, that's when we reject the null hypothesis. Okay, so this picture helps give the flip side confidence interval where we're looking in the middle, and then in the hypothesis test we reject when this value of t falls in the tails, because that gives us evidence that this t distribution is not consistent with the data. Okay, so the data tells us, gives us evidence against a hypothesis or for a hypothesis, but it doesn't tell us directly whether that hypothesis is true or not. And so that's why when we talk about hypothesis testing, we try to be quite careful. We do not claim that we know whether the hypothesis is true or not. We are looking at whether the data, so given the hypothesis, is the data consistent with it or not? Okay, so that's a subtle point, but important in terms of interpreting the results of hypothesis tests. Okay, so we calculate this test statistic, and then finally we reject the null hypothesis at a specified significance level. It's called alpha. If the absolute test statistic exceeds some threshold C. So again, we have to define C, and that's going to depend on, again, the significance level alpha and also the reference distribution from which we are testing. Okay, so C where. Okay, so remember these are just flip sides of each other, so it's the same C in this case. It's the 1 minus alpha over 2 quantile of Tn minus 2. And then corresponding to the actual outcome of the hypothesis test, we also have the p-value. So again, p-values can cause quite a bit of confusion in terms of their interpretation. Again, p-value is not talking about the probability of the hypothesis itself, but it's talking about the probability of seeing a test statistic as extreme as seen in the data. And so, okay, so given the computed value of the test statistic, we can calculate the p-value to be the probability that this t distribution is, so in words, is equal to or more extreme as the observed test statistic. Okay, so it can be written in this form. And because of the t distribution symmetry, we can also write it as 2 times the tail probability. So 2 times probability that ditch the absolute value that t is greater than or equal to the observed absolute value of t. So that's the p-value. Okay, so I'll add that to the picture. So for example, if you calculate t here, and it's let's say this is the value of t, then your p-value would be anything that's more extreme than t. So you can either be more extreme on this side, and then you can also have the corresponding by symmetry of minus t. So it would be the red area would be your p-value. Okay, so that gives you a basic recipe for carrying out confidence interval calculation and hypothesis testing after we have derived these properties, distributional properties of beta 1 of the estimate of beta 1 as a random variable. Okay, so I will pause here for a moment to see if there are any questions, and then we will call it a day. So if you have any questions, please let me know in chat, and I will answer them before I log off. So there's a question about the sum of squares x, but I don't know when that was actually written. So in the test statistic, okay, so let me just explain, so hopefully I get what we're saying. So standard error is defined as, according from the last page, so standard error beta 1 hat is sigma hat over root as sum of squares x. So that's the definition of the standard error from the previous page. Okay, and then there's another question, which is why do we capitalize the y's for a beta 1 hat distribution and not the x's? Right, so in the beta 1 hat, okay, so it's not on the board anymore, but when we wrote that, so when we calculated beta 1 hat as a value, we used lowercase for x and lowercase for y because we're plugging in the observed data points. And then when we moved to inference, I changed the y's in that expression. I said, let's view beta 1 hat as a random variable. And so I replaced the y's with uppercase y's so that we can calculate its mathematical properties. In that case, though, x is still, we're still assuming throughout that the values of x are simply observed. So we're not going to put any probability distribution on them by assumption. And so that's why throughout all the calculations, we continue to assume that x is constant and doesn't have a distribution, so they're all lowercase. And then there's a question about how do we get 1 minus alpha over 2 quanta. Okay, so the t distribution is symmetric around 0, much like the normal. It has fatter tails, but otherwise you can still use the symmetry properties. So the area from 0 to c is the same as the area from minus c to 0. And so if there's 1 minus alpha between minus c and c, then also the tails are also symmetric, and we have alpha over 2 on each side of the left and right tails. Okay, so I think there are no further questions for now, but if you do, just let us know on Piazza, and we will respond to you. We'll respond to you there. All right, so I will log off for today, and then I will be streaming again on Wednesday at 10:30.